Hello everyone, welcome to the CosKASI ECR seminar. Today, it's our pleasure to have Mehdi Rezaie from Kansas State University. Mehdi did his PhD in Ohio University and now a postdoc in Kansas State University. Today, you're going to talk about his research about handling observational challenges in the era of big data cosmology. So Mehdi, please start when you're ready.
Great, thank you very much. And it's a pleasure to be here. And I'm very excited to tell you about the research that I've been doing for the past few years since I started my PhD. And it's nice to see some familiar faces. And at any time, please feel free to interrupt me if you have any questions. So today I will tell you about how we go about handling observational challenges when we try to do cosmology with larger scale structured data. Okay, before going through the details, I wanted to draw your attention to this quote from Feynman that he says, "It doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong." And one example of this in recent years is, I think that was when I started working with Armand back in Pohang. So there was this paper which made a lot of news, and they claimed that have detected power in the power spectrum of the CMB polarization map. And if you go based off of Feynman statement, there are two models, and we have observation, these data points, and we can say model A is wrong because it doesn't agree with data, and data prefers model B. So, but that being said, later if you go to YouTube, there is also people celebrating this detection and whatnot. But let me also turn this off. But later, based on further analysis, it was revealed that this signal was indeed due to unforeseen effects because of Milky Way extinction or dust. So that being said, it's, we are living in an era which is when it's very, the data is very big and the complexity of the data is enormous. So we have to be careful how we clean the data to kind of measure some statistics and then extract insights from the data. So the survey that I will talk mostly about is Sloan Digital Sky Survey, or as known as SDSS. It started in 4 different phases. It was supposed to be 2 phases, SDSS-1 and SDSS-2, which led to the discovery of baryon acoustic oscillation feature, and then it attracted more funding, and then there was a follow-up program called Baryon Oscillation Spectroscopic Survey, or BOSS, which enabled 1% measurement of the distance. And because, again, the program was so successful, they extended the program as known as eBOSS, which lasted until late 2019. And one major update in the latest program was they targeted a new class of galaxies as known as emission line galaxies that are roughly young galaxies with active star formation to fill the redshift gap between quasars and low redshift galaxies. But how did they go about doing this? They drilled like holes in this plate, and each hole corresponds to a target on the sky to collect the spectra and guide it to a spectrograph. This is the spectra of, for instance, of a quasar at redshift 1 almost 17. And there are distinct features that help us to identify the redshift for this particular object. And at the bottom, for comparison, this is also an observed spectrum of a galaxy at redshift of 0.04. And this is also a cartoon on the right done by David Kirkby that illustrates how these targets are separated in a 3D space by redshift. So this is like the gap that I was talking about, that which was addressed by the new emission line galaxies. But how do we go about extracting information from this data? So this is a cartoon that has exaggerated the feature in this data set. So one simple statistic is to use 2-point function, and assuming isotropy, one could design this estimator, which is 2-point function of the catalog of galaxies relative to 2-point function of a catalog of random galaxies that don't have any clustering, but they just represent the survey. And by measuring this statistic, at the bottom, you see this correlation function times separation squared as a function of separation. And you can see that there is a favored scale, which corresponds to baryon acoustic oscillation, which is also exaggerated in this plot on the right. And if you think of this as a Fourier transform, this will transform to a series of oscillations in the Fourier space or in power spectrum. But the applications for this feature is that if we know that there is a standard ruler at some distance, and we know this size of this ruler from cosmology, we can look at it at different epochs or times or redshifts, and kind of constrain the expansion history of the universe, or in other words, dark energy equation of state. And to put into perspective the amount of work being done in 2 decades of cosmology done by SDSS, this is a plot done by Ann and Rachel. And on the right, these are the correlation functions from different tracers that were observed by different subprograms within SDSS. And the emission line galaxies are these blue ones, which are attempting to fill the gap between quasars and galaxies. But that being said, as I mentioned earlier, there is a challenge that I wanted to draw your attention to. James Peebles, from his paper, he says in any catalog of extragalactic objects, the apparent density almost varies across the sky because of variable effects of galactic obscuration and confusion. This is what I was trying to mention. Like, this is the Milky Way in the background, and this is the telescope in Chile, the Blanco telescope. So while we are trying to take images of the sky, we are also subject to external realities, for instance, Milky Way extinction, or stellar, like local stars, or the turbulence in the atmosphere. So these are all external properties that can induce spurious fluctuations in the observed galaxy density field. And if we want to measure something and to answer some cosmological question, we need to make reliable correction for these effects. So in the rest of my talk, I will try to focus on this challenge. Are there any questions so far? No. Okay, so I mentioned because of these realities, we would have spurious features in the density field, and as shown in this plot on the top, which are emission line galaxies, targets. You can see that, from cosmology, we know that the universe is homogeneous and isotropic on larger scales, but when we look at this plot, we see that there are some larger scale fluctuations, and which don't seem to have physical origin. So, for instance, you can see that these features highly correlate with the map of extinction, some of them. And this one, for instance, highly correlates with a sub-survey, which, for instance, was observed this part of the sky. So there are various effects that go on here. And one traditional way that people try to mitigate these effects is regression, or the simplest way is linear regression, linear multivariate regression. And the way it works, we do have some templates. For instance, extinction, which I mentioned, anyone could be the survey depth, like how deep a survey can go, like depending on the exposure, how faint a galaxy can be detected. So this is equivalent to a concept called depth. And you can see that this part of the sky was deeper because that was done by a different telescope, so it went deeper. And when we compare these templates just visually by the observed density map, we do see some correlations. But if you want to do it like quantitatively, this is the whole pipeline. We have a model that can be like a linear multivariate model, and it takes these templates as input, for instance, X in this case, in this notation, and some parameters. And this output is compared with the observed density map by the optimizer to kind of provide feedback to the model to tune these parameters, these thetas. Doing this process iteratively, the model will learn to produce something that almost looks as close as the observed density map. The subtle difference is these maps don't have any cosmological information, and therefore whatever we learn is just purely those spurious fluctuations. And once we have this map, which we call it selection function, we can use it to undo these effects and get a more homogeneous map. The idea was we don't know exactly how these templates kind of affect our observed density map. So the idea which I worked on as my PhD dissertation was to use a nonlinear approach. And a good example for this is just using neural networks, because they are universal approximators, so they can model a wide variety of functions. And this was like the perfect problem to be tackled with a neural network. So the architecture is, we do have our imaging properties in the first layer, and these properties are connected to neurons, and each neuron could be like a simple linear model with a difference that it also has one activation function. So each neuron takes these inputs from the previous layer, does a linear algebra, and then applies a nonlinear function and returns the output to the neuron in the next layer. And so the information flows from left to right, and at the very end, we have a prediction for the number of galaxies. But as I mentioned, because these inputs don't have any cosmology information, what we get for the number of galaxies will be just the expected mean number density of galaxies, or our selection function. which was this map on the top. And you might wonder why this works. So the neural net, each layer is like a folding operator, which uses symmetry in the parameter space to simplify the problem. So if you want to like classify these circles from those crosses, it's kind of difficult to do it in this stage. But if you fold this paper 2 times, the classification will be simpler. So this is like one idea that why a neural network architecture simplifies the problem into a linear problem. And at the latest layer, it's like a linear regression. And one other advantage is that it can also replicate multiplication. So you don't have to feature engineer to multiply 2 inputs, like if you need to, unlike other classical machine learning algorithms. And it can also model a wide range of models. So in this plot, in the panel on the right, I'm showing how a neural network can be trained to model a quadratic function with noise, or a sinusoidal function without noise, for instance. And if you want to like read more, there is a nice paper written on how these piecewise linear function, when they are put together, they can model any trend. But you might wonder, okay, show us some cosmology and how it works. So this is like the first attempt of using a neural network-based treatment. And I show the power spectrum as a function of angular scales. So left side is large scales, right side is small scales. And you can see without correction, we do have large power at large scales or low multiples. And as we treat the data, we get lower power. So this is similar to what I showed at the very beginning related to the CMB measurement. So you can see that only changing the model that we use to mitigate these effects, we get a reduction in the power. So if you want to do cosmology, so it's very important to get a handle on these effects. So this work was also utilized in a collaboration with Pauline. In this work, we wanted to cross-correlate imaging galaxies with spectroscopic quasars. And because we wanted to increase the overlap, we had to design our own selection, which like pushed the boundary and it increased the systematics in the data set. And as you see in the bottom panel, if you look at the mean density of galaxies as a function of Milky Way extinction, we see that there is a nonlinear trend in the data. So this trend should not be there because the galaxies that we observe should not depend on the Milky Way as a foreground, but that's what it is, and we need to take care of it. So you can see that if you use a standard multivariate regression, we get this dashed line or dotted line, depending on the complexity of the linear regression. But if you use a neural network approach, we are able to indeed mitigate the effects below 2%. And with this technique, we were able to get a better measurement of distance using cross-correlation than autocorrelation quantitatively, 5% versus 9%. So this will be very useful for doing cosmology with deeper photometric galaxies and denser spectroscopic samples with future surveys. But looking further into EBOS quasars, this is the power spectrum that we get as a function of wave number, and on the high K it's linear and on the low K is log space. And you see that these are baryon acoustic oscillations, which I introduced earlier. So the dots are the data. The squares are, again, the data without treatment. And the solid line is the mean of simulations, which are based on lambda CDM. And as you can see, the data doesn't agree with the mean of the mocks. So one question that might ask, even after correction, we see that the data doesn't agree with the mocks. So one question that we could ask is that, are we detecting a new physics? But if we use a nonlinear approach, we see that indeed we mitigated that excess power. So this is why using a nonlinear approach is crucial, especially if you want to use a larger scale or low K part of the spectrum. And you might wonder, okay, tell us more about the details. So this is like the plots of the data using a standard treatment in the very left panel. And next to it is we have the nonlinear treatment. The differences is kind of hard to tell, but if you take the residual, we see that there is some noise, but also there are some larger scale residual differences. And if we look at the extinction map, for instance, we see that some of these trends actually line up with extinction, as if the standard treatment was not properly accounting for the dust effect. So that was like kind of a visual story. If you want to get more quantitative, we can group these pixels of the sky into bins given their value of the extinction. And in each group, we can measure the mean density and then subtract the overall mean to get the mean density contrast. If we look at the data, we see the black line before treatment. And if we measure the chi-square relative to 1, we get around 375 with respect to 8 data points, which is very large. If we apply standard treatment, we get these blue circles, which are relatively near 0, but still there are some deviations. And if you look at the chi-square, it is around 37 given 8 degrees of freedom. So this is like quantitative way to say that there is residual effects, at least against extinction. But using the nonlinear approach, we are able to mitigate that effect such that the chi-square is dropped to 9.9. We can do this against all available templates and get a total chi-square, which I'm showing in the bottom panel, and compare it with histograms that we can get from simulation. And we see that relative to simulations, the standard treatment doesn't return a good p-value, as if there are not many simulation or mark realizations that have similar fluctuations. Or in other words, there are significant systematic effects in the data if they use a standard treatment approach. There is also another statistic based on cross-power spectrum, and it also shows the same issue with the standard treatment. But would this matter for our physics, in particular for BAO? We did a work with Grant Mertz, who is now a graduate student at Urbana-Champaign in Illinois. And we looked at the effect of these treatments on the BAO parameters, in particular a parallel or a perpendicular. And we observed that relative to the precision of, for instance, in this case, EBOS, they are not significant, but they could be significant for DESI, or dark energy spectroscopic instrument, which then requires further work. And there has been parallel efforts to kind of characterize these effects for DESI. But it could be important for physics that is sensitive to larger scales or low multiples, for instance, local primordial non-Gaussianity. In this plot, I'm showing the angular power spectrum for different values of the parameter FNL, and FNL is a deviation from Gaussian fluctuations, a quadratic deviation, which has been shown that it results in a scale-dependent shift in the bias that connects dark matter density fluctuations to galaxy density fluctuations. So this is a work that we did with Eva. On the left, we have the posterior of FNL from EBOS quasars using the nonlinear treatment. There are different ways of using optimal weights to assign more weight to quasars that are at higher redshifts, and this is an attempt to take care of the redshift evolution of the bias. And you see that whether or not you account these optimal weights, the posterior is not very different. But if you use the linear treatment, depending on whether or not you assign more weight to high redshift quasars, you get different posterior on the FNL, which is alarming. And if I unblind the data, you see that the effects is huge given the precision that we are working with. And this is like a summary of our measurement compared to previous measurements. So if you wanted to use a standard treatment without optimal weights, that would have indicated that we measured excess power or FNL greater than 0. But with our treatment, we are able to get consistent measurements with lambda CDM or Planck measurement. But what we learned from this practice was that nonlinear models work better than linear models. For instance, in the panel on the left, I'm comparing the standard treatment, which was a linear approach, with my own implementations of linear regression and neural network nonlinear regression using various cos functions. And you can see that the linear models are similar, but when you go to nonlinear models, you get this significant shift such that it also results in significant impact on the power spectrum if you look at the power spectrum in the bottom panel. And on the right was also the other point, that it's crucial to have useful templates. So the standard treatment in EBOS pipeline uses a stellar density from its own survey. But as you look at the trend of quasars relative to stars from the Gaia program, you see that there is a residual trend. And if you use the Gaia template, we are able to actually mitigate this trend and get a lower power spectrum. So the panel on the right just indicates that it's crucial to have a template to mitigate that effect. And this also goes back to my earlier slide where in the CMB measurement, they had attempted to correct for dust. It's just that they didn't use a good template. But that being said, now I want to shift a little bit toward dark energy spectroscopic instrument and the challenges that I'm currently working on. So dark energy spectroscopic instrument, or as known as DESI, has started collecting data, and it's going through the analysis of the first year data, and it's going to release the biggest 3D map of universe up to date. And the way DESI is doing it is using robots to collect up to 5,000 of spectra all at once, simultaneously. And with this technique, DESI has been able to catch up with STSS after only 7 months of observations. But, you know, with great power comes great responsibility. So because DESI is bigger, observes a bigger footprint, and it utilizes targeting of fainter galaxies, the galaxies could be subject to a more severe systematics. So one of the works that I've been doing, for instance, you see here the selection function of DESI luminous red galaxy targets in this part of the sky, and you see that we are able to predict the trend and mitigate the trend. But this is only one realization of selection functions. So one thing that you might wonder, okay, so what is the uncertainty in the selection function? So one approach that I worked on was, instead of optimizing like traditionally, going from some random point to the global minimum, you use a cyclic learning rate to take snapshots of the model. With this technique, you only train once, and you can get, in this example, you are getting 3 snapshots. So this will allow you to create an ensemble, and then you can use that ensemble to estimate the error. So this is what I worked on. So for instance, there are 3 examples of selection functions for a single data set. And on the left panel, I'm showing 100 of them. And these lines are models that agree with the data. And the red ones are when I use those models to mitigate the data. And so this work with Tanvir, we adapted this technique to kind of answer the question, if there is additive biases from our estimation of the survey selection function, what would be the effect or impact on cosmological parameters? So this was like one example that we cross-correlated MARC data following DESI emission line galaxy characteristics with Planck CMB lensing. And we show that if we have additive biases in our selection function, that could result in significant, that could kind of propagate to our cosmological parameters. We are working on a accompanying project that we are going to use real data from DESI targets with CMB lensing to kind of look on sigma 8 or growth of a structure parameter. So please keep an eye out for that paper. But there is also one work that you might wonder, how can we learn about what is about the inputs that is telling the neural net the trend, or like along the lines of trying to explain the method. So there is a technique called recursive feature elimination. So you pick one feature, let's say number 2 in this figure, and you remove that feature and you train your model and then evaluate how your model can predict. You put this feature back and remove another feature, for instance, bottom left, and you train and evaluate on the validation. And you realize that if you remove feature number 2, your model won't perform worse. So it's an idea of reducing the dimensionality of the data without damaging how well your model performs. So this is an iterative process. And what it does, it sorts your features based on importance. So from top to right, we have one iteration of this process. And from left to right, we have these features sorted based on importance. So you see that for that particular data, which I presented earlier, stellar density turned out to be one important feature, whereas sky brightness in the R band was turned out to be unimportant. As if you remove a sky magnitude or sky brightness, your model won't, you won't observe any lack of performance in your model. And I applied this on set of simulations which I had contaminated, and those maps that were used for introducing the contamination are noted with these stars, and you can see that we are able to kind of identify most of these maps. And for real data, for two different tracers, blue galaxies are more contaminated compared to red galaxies, and you can see that more properties are identified as source of contamination in the upper row. There is one work that I'm doing in collaboration with Jayashree Vera, who is a PhD student at Kansas State. We are trying to use L1 penalty, which includes some of the absolute coefficients from the first layer, to put a constraint and remove the degeneracy in the parameter space. And by doing so, we can look at the sum of the absolute weights of the first layer to see what features are important. So the higher the weight, it means that particular feature has higher importance. And she was able to get similar results by using only 9 features. So she reduced the dimensionality by almost 50%. Still got the same clustering. So to wrap up, what I showed was like one prime example of how we can tackle systematics. And I hope I convinced you that the work on systematics is not a one-person job. And there are many facets that need to be treated. And most of the codes and catalogs that are prepared for common cosmology, like BAO, may not be appropriate for primordial non-Gaussianities. For instance, the example I presented was the quasar, EBOS quasar catalogs, and the standard treatment, which indicated there are residual systematics. There are more simulations with sophisticated systematic effects to validate our methods, nevertheless. But overall, thinking about neural networks or deep learning-based models, we can model nonlinear relationships, in particular in the problem of handling imaging systematics in galaxy survey data. But also, as physicists, it's, we always want to know what's going on. So we don't want to use it as a black box. So the last few slides, I presented my efforts to try to understand what features are very important for our task to kind of understand and help us interpret the results. And last but not least, I wanted to also thank and acknowledge the support I have received over the years, but in particular, Ohio Supercomputing Center, which for EBOS work, I use about 380,000 CPU hours, which is crazy if you turn it to years. So I was able to do all of that using supercomputer plus computing. And with that, I will be happy to take any questions.
Right, thank you, Mehdi, for a really interesting talk. Do we have some questions from the audience? Right, Mikhail?
Yeah, hi, thanks a lot for the talk. I really enjoyed it. I have a question about the recursive feature elimination method that you showed at the end. It's not a question, it's more me probably understanding things incorrectly. But you were mentioning that you are removing one feature at a time, right? And I was just thinking, because you put the feature back, I was just thinking in the back of my head, what happens when you have information that is correlated between several features? Because you can take one feature out and the model still works good because information is in the other parameters, right? And so at the end, you come out with the idea of like, oh, I can take these 5 parameters out, but in reality, there was information in those 5 parameters. It was just correlated, so you were finding information between them. I don't know if I explained that correctly, but
no, that's an excellent example, and one example of that correlation is extinction and stellar density, because they both follow the structure of the Milky Way. So wherever you have higher a region with a higher density of stars in the Milky Way, there is more likely to be dust, and there is more likely to have high extinction. So these properties are correlated. And what you mentioned is like one caveat is that, if features are correlated, there will be leakage of information from one to the other. But this is the best we can do at the moment, and we are comparing how the model works on validation set. So as long as the model works on validation set, so this is a residual in the root mean squared error relative to the validation set. So as long as the model is doing well on validation set, we don't care if removing a feature doesn't impact the performance.
okay.
Like if we keep all of these features, the benefit will be more than the cost, because if we use so many features, we are likely to regress out some of the true clustering. So it's like a risk and reward. So we want to minimize the risk of overcorrection, over regressing out the clustering information. So therefore, we don't mind if one feature gets kicked out because it was correlated with another map.
I see. Thank you.
Right. While others form their questions, I have a question myself. From slide 20 on, you showed us this difference between the neural network treatment and the linear treatments, and seemed very effective on doing all these systematics. I was wondering, maybe I've missed, but I wanted to know exactly like how this is done, like what kind of training data set has gone in, and in which part was this neural network used to approximate. So yeah, could you elaborate a little bit more?
Yeah, thank you for asking that question. So let me go to this plot. Yeah, so the thing is, there are also some other approaches that train the models on simulations and apply to data. But the technique that I utilized in this work is 5-fold cross validation. So I split this footprint into 5 equal size chunks, and then with a permutation of 3 out of 5, I select 3 chunks for training and I leave the other 2 for validation and testing. And there are 5 ways you can select 1 out of 5. So by doing this 5 times, it's time consuming, but we want to train the model on the data, not simulations. So by doing this 5 times, we have tested the model every time on a different chunk. And at the end of the day, if we pull together all of these 5 chunks, we can reconstruct the result of the model when it was tested. There is no overlap between training and test sets. And that's the important part when you design the training and validation and test sets. But with that technique, we don't need simulations to train the model. So this is the data, you train it on the data and you get the result and you clean the data directly at the cost of extra computing time.
Sorry, I might be misunderstanding something. But so you have a previously cleaned data set where you already know NG, and then you are feeding all of the parameters that you use for cleaning and try to reproduce NG, right?
So the thing is, we don't know what the true NG is. What we know, we have it observed NG, and we kind of regress out this observed NG against some templates. But because these templates don't have any clustering, like cosmological clustering, what we get doesn't have that clustering information. So we don't need to have clean NG. We just take the data that has true cosmological NG and systematics, and by regressing against templates, that cosmological term will be treated as noise, because the model is told to kind of use these templates as proxy. So whatever is in the observed NG that correlates with these templates, that's what the model is going to learn. So it's important to have templates that don't have cosmological information, because otherwise the model will learn clustering. And when we do this cleaning, we are also going to remove like unwanted clustering signal.
Right. Yeah, thank you for that clarification. I think I misunderstood before. While others come up with some questions, I was wondering, so if we find that the neural networks, because you use the actual data, not the simulations, to train these, I guess the hope is that it is picking up systematics that's not necessarily simulated in the MOOC data set. Is there a way that you could quickly tell, like from these neural networks, that there are systematics that hasn't been put in the MOOC data? Makes sense.
There are, that's where it becomes cosmology dependent. So let me show you some, I don't know if I have it here. Yeah, so this is like a work that I'm doing at the moment with DESI data. And there are ways to kind of gauge the level of systematics in the data and in the mocks. The limitation is if we have some systematic that we don't have the template for, we are not going to be able to kind of mitigate that effect. So that's a limitation of regression-based methods. They rely on templates to mitigate the data. And like based on these plots, you see that the data is in agreement with simulations, and these simulations don't have any systematic in them. But when you go and look at the power spectrum, we see that there is still some residual power. So this residual power could be either some systematic effects that we don't have the template for, or there could be some sign of new physics. And I think that's what makes it exciting. So we need to look for ways to design new templates. But to answer your question, like to recap, there is no way to tell whether or not you have systematics, some unknown systematic, or there is a clustering signal in the data. And that's where other methods like forward modeling selection function based on simulations, like simulating artificial galaxies and running your images with synthetic galaxies through the pipeline to forward model the selection function. That's like one way to get selection function, which complements what I presented today. But the disadvantage of those methods is that they are very time consuming. So one run could take weeks, if not months. Yeah. I hope I answered your question.
Yeah. Good. Thank you. Are there other questions? Sorry, another quick question in that case. All right, thanks. Yeah, so at some point you compare like linear approaches with the neural network treatments, but you kind of emphasize that neural networks are non-linear approach. I was wondering if other non-linear approaches that are not neural network would give similar performance, or you still expect neural networks to perform much better in those cases?
Yeah, that's an excellent question. The methods that I'm aware of are, for instance, random forests. Random forests are ensemble of decision trees, which are designed for classification, but their application has been extended to regression as well. There are some work done by my collaborators based on random forests, and random forests are also great universal approximators that they can also model nonlinear relationships. But the issue with random forests is that they can't extrapolate because they don't have a functional form. If your region of test is outside of the region of your training, and the random forest is just going to predict one constant. Whereas the neural net can be considered as a parametric approach, which depending on how well your data behaves, you can rely on the extrapolation. That's one advantage, but also, training neural networks is more time consuming than random forests. So I think the good thing within DESI is that both methods are used. So we can kind of gauge the differences and benchmark how well one method outperforms the other. And there are like other subtle things, like how the implementation is done, like what's the cost function that was used to train the data. For instance, one method would work for a dense sample of galaxies, but the method might not work for a sparse sample of quasars. So the problem, as I mentioned, is not a one-person job. So like if someone does this for galaxies, another person needs to redo it from the beginning for quasars, because the way systematics appear in these tracers are not the same, and the same code cannot be applied to both tracers out of the box.
Right, yeah, thank you. Stephen has a question.
Hi. Hello, Mehdi. How you doing?
I'm good. Yeah, good to see you.
Yeah, good to see you. Yeah, long time. Thanks for the talk. It's really good. It's a really nice talk. I have a really naive question. I don't know about this stuff, but so there's a paper some time ago with Sube Sarkar found a number density dipole in quasars, right? In not a different data set, and so what that tells you, if that's correct, is that the number density of these objects will vary as a function of galactic latitude. But also you found a correlation between the number density and the stellar density, which will also vary as a function of galactic latitude. So in your approach, would that sort of signal, if it is a signal, would that just be absorbed into your selection function? So are you kind of, could you accidentally absorb a signal into a selection function with your choice because you've made some sort of implicit assumption that the data is isotropic?
Yeah, that's an excellent example. Yeah, indeed. If there is some cosmological signal and that correlates with one of our templates, the model is going to catch that, and the model is going to like regress that out of our data. So we are going to like remove that signal. And I think that's something that my recent paper, we have been working a lot on trying to see if we are going to remove FNL signal if it correlates with our templates. And indeed, we found that we are going to remove some of the signal, and depending on how many templates we use, that reduction of the true signal is going to be larger. And that all indicates it's not just a constant shift, it's a model dependent effect. And we need to have mocks with different, in this case, values of FNL to calibrate how big is the shift. Let me show you this plot. This is what I'm trying to, so this plot, do you see my plot?
Yeah.
So this plot is, I got FNL from simulations that were run through the pipeline and compare it with the value of FNL that I measured from the same simulations that I didn't apply the pipeline on. And you see that there is a shift, and depending if I use more maps, this shift will be larger, and it's not a constant shift, so it has some slope. So we try to use simulations to calibrate the effect.
I see. So if anyone ever finds some cosmological signal, you have to basically simulate it and then run it through your pipeline to see what your analysis pipeline will do to that signal, to check if it's removed. Yeah.
Exactly. Yeah, that's what we did. For EBOS work, we realized the effect is around 10 FNL, delta FNL of 10, which is lower than a statistical precision. But for this work, we realized the effect is larger. So therefore, we attempted to come up with some way to kind of recalibrate our measurement.
Really great. Thank you very much. Thanks.
Thank you. Appreciate it.
Thank you again, Mehdi, for a really interesting talk. I think the time's up now, so I'll stop the recording.